You wake up in the middle of the night and you tell yourself, what if? With enough what ifs, anything seems possible. So maybe it would be possible to turn off the sun. Behind every seemingly seriously dumb question, there's a whole bunch of incredibly satisfying answers. First, to really grasp the enormity of the project we're tackling, let's state the obvious. Trying to turn off the sun means facing a huge problem. Here's our star compared, to scale, with our planet. Assuming the planet was made entirely of water, it would mean almost nothing to the sun. In terms of mass, it would be like a big drop of water to you. By the way, that much water would contain far more than there is in our entire solar system. And most importantly, let's state the obvious. The sun is not a ball of fire. In a flame, the energy comes from chemical reactions. It is released when molecules combine and break apart, exchanging electrons to create more stable variants. Liquid water, for example, helps fight fire because, being energetically stable, it absorbs heat and deprives the fire of part of its ability to sustain combustion by turning into vapor. Except that, unfortunately for our experiment, stars do not burn in the same way as a flame does. They are the site of reactions of a completely different nature, which do not involve a rearrangement of the electronic bonds between atoms, but rather the nuclei of the atoms themselves, in processes known as nuclear fusion. Let's get to the heart of the matter. Let's imagine that, as if by magic, we have, say, a drop of water the size of our star, and a super pipe capable of drawing from this reservoir to continuously water our star, sending it, let's say, every second, a volume of water equivalent to that of all our oceans. At the start of the experiment, the sun's outer layer at the impact point will cool slightly, as vaporizing the supplied water and breaking its molecules requires energy. And for a while, the surface of the star will be the scene of chaotic turbulence. But underneath, at the center, the engine of the sun, its core, keeps working as if nothing happened. Worse. It will even soon ramp up, because you have to understand that our sun, like all the stars in the universe, gets its energy from transforming light atoms into heavier atoms. At its current stage, its fuel is hydrogen, and as you might have guessed, water contains a lot of it. So, in a way, watering it is like providing it with fuel, although the term fuel isn't really appropriate here, but it's supplying it with raw material to fuse. And here's where it gets interesting. At the end of the process, you end up with a sun that's twice as heavy as it was at the beginning. And so, it's much closer to its death, because the more massive a star is, the faster it burns the candle at both ends. In a way, far from having extinguished the sun, we've simply pushed it faster toward its extinction. And by speeding up its life, we've hastened its death. Because while our sun still has about 5 billion years of activity ahead of it, doubling its mass reduces its lifespan to just 1.7 billion years. The problem here comes from the fact that the star, having become more massive, has compressed under its own weight, and in doing so, its core increases in pressure, then in temperature. And the rates of nuclear fusion taking place there skyrocket in turn. Let's take a ridiculous detour. The fact that pressure and temperature are closely linked is at the core of the process that ignites stars and triggers fusion reactions in their cores. And this has an amusing consequence for our hypothetical drop with the mass of the sun. If it isn't emptied very quickly, then, under the force of gravity, this insane amount of water will collapse in on itself until, at the center, the pressure, and therefore the temperature, eventually exceeds a threshold capable of igniting a thermonuclear reactor. And then your water bubble would start to shine, because it would have become a star itself. And it's actually amusing to think that, in theory, you could ignite a star with just about anything. The same thing would happen if you gathered a solar mass of wood, alcohol, or even sunscreen in one place. End of absurd aside. But let's get back to our water-soaked sun. Where it gets really striking is that after emptying the tank, we end up with a star that's hotter, with a slightly blue-white hue, and emitting intensely in the ultraviolet, to the point where it's become nearly 12 times brighter than our own. This star with two solar masses is unlike anything else in the known universe, because it's unusually rich in oxygen atoms. To the point where these now account for more than a third of the mass of this star, which now draws most of its energy from a type of fusion different from the one currently happening in the sun. In fact, the sun gets its energy from the transformation of hydrogen into helium, using what's called the proton-proton fusion reaction. But for stars whose mass is more than 1.3 times that of the sun, the carbon-nitrogen-oxygen reaction becomes the main source of energy. In any case, trying to put out the sun by wetting it is a bit silly. We've just made it bigger, brighter, and hotter. And since it's the nature of the atomic nuclei that fuel it that matters, not the chemical properties of combustion, well, trying to put it out with a mass of gasoline or dry ice would have the same result. That is, to make its internal fire explode, to fan its flames by feeding a beast that has become 12 times brighter than our star. And in the wake of this increase in brightness, it will quickly burn up all forms of life on Earth's surface before boiling our oceans. Maybe we shouldn't have done that. Let's try to fix this mistake. Well, we know that stars get their energy from fusion reactions in their core, where pressure and temperature allow them to overcome the repulsive forces of atomic nuclei. Maybe there are elements that, by their mere presence, could put an end to these reactions. To try to extinguish our growing problem, we can subject our star to an intense dose of iron by throwing in 2 solar masses of it. This heavy element, the ultimate fusion product of stars, has such high nuclear stability that it acts somewhat like an energy sponge. Anyway, on paper it might seem like a good idea, but once again, don't get too excited, it's not a sure thing. Because even if iron is going to pollute the core and slow down the fusion reaction rate there until it eventually stops. So rare that the process becomes unable to sustain itself. When the fusion reactions stop, the star, no longer able to counterbalance the contraction of the outer layers with radiation from the core, will begin to collapse. And the contraction will increase the pressure, and therefore the central temperature, and ultimately that of the surroundings of the metallic core, to the point of eventually creating conditions there that allow light elements to fuse, thus restarting a thermonuclear fusion reactor. A vicious cycle. The star has gone out, then reignited right after. And so, we end up with a star that now has a mass of 4 solar masses, with a lifespan reduced to 300 million years and a luminosity nearly 130 times higher than that of our current sun. We'll have to instantly think about getting out of here. Missed it again. In short, we can clearly see here that the monumental mass of the star is in itself a big and bright problem for achieving our goals. Because this mass is an immense reserve of gravitational energy, and in the end it doesn't matter how much water there is or what we throw into it, except that hope is always the last thing to die. So let's take our pipe again, this time with an extremely fast jet in mind, to try to blow out the sun like an ordinary candle. Or more precisely, to peel it like an orange, by removing its outer layers. Let me explain. By spraying any kind of material onto the upper layers of the solar atmosphere at speeds close to the speed of light and at the right angle, we could tear away part of the star's outer layers. If we do it right, by coming in and essentially sanding down the surface of the star, scattering part of its outer layers into space, we should gradually decrease its mass and as a result, reduce the pressure and temperature at its core. Assuming we were able to tear away the equivalent of a lunar mass of material per second, it would take us more than a year to achieve our goal. A year during which we would see the brightness of our star, subjected to such a dangerous and drastic abrasive process, decline, shifting from orange to red, before finally disappearing from the visible spectrum. Yes. Still, make sure to aim the pipe properly to ensure you blast the layers of gas away at speeds greater than the sun's escape velocity. Because otherwise, you could end up with a cloud of gas that's dense and heavy enough to collapse in on itself and reignite a new star. Damn it. Well, the problem is that, to put an end to all thermonuclear fusion processes in the world, we'd have to peel our sun down to the core. Because it's only after being stripped of a little more than 92% of its mass that the star would become a brown dwarf. A celestial body considered a failed star, too light to shine in the visible spectrum. Hooray, mission accomplished. We've peeled and therefore extinguished the sun, and now we're freezing. Well, here, we used a technique that consists of stripping the sun until it falls below the minimum mass required to ignite a star. But we could also have chosen the so-called upper limit method. For that, nothing could be simpler. You just have to keep feeding it with anything and everything. Basically, to multiply the already mentioned amounts by at least 10 so that the sun reaches a point of no return. Beyond which, in a few million years, it will end in a gigantic blaze of joy and sadness, exploding in our faces as a magnificent supernova. After that, the problem is that even by multiplying its current mass by 10, we would still have to wait nearly 30 million years before seeing it explode. Unless we can get our hands on more than 1,000 stars with a mass comparable to ours, and then quickly throw them all into the sun. And what's amazing is that with 1,500 solar masses we would get a huge star, an understatement, that should collapse in on itself without even going through the supernova stage, and that would happen in less than a century. Well, keep in mind to take a step back, because the behavior of this type of star, which we think existed at the beginning of our universe, is still not well understood. We're working with models. And all things considered, maybe it wasn't worth waking up for this. Because the simplest way to extinguish our sun is still to do nothing, to just sit there and simply be patient by letting it evolve on its own, like a grown-up, for another 5 billion years or so. Inevitably, there will come a day when the elements available for fusion will run out. After exhausting its hydrogen reserves in its core, the star will start fusing helium and turn into a red giant. A star that will eventually lose its outer layers by itself, creating a planetary nebula at the center of which will sit a white dwarf. A very small star that is a star in name only. And although it will remain extremely hot on the surface for billions of years due to the heat stored during the explosion, it will no longer be the site of nuclear fusion reactions. Finally, with my mind at peace, I can go back to bed, because this remnant of vanished stars will already be extinguished in the strongest sense of the term. And if you ask what the point is of knowing all this, the answer is absolutely nothing. It just feels good. Thank you to everyone who, by supporting us on Typee, Utip, or through the join button, allow us to occasionally look into such delightfully absurd questions without getting lost in them. To learn a bit more about stars, click here, and to dive into the sun, go over there.